All right, now that we've finally gotten out of calculating the capacity, we're actually going to design beams. So, you go down. Okay, so we're basically going to design, this is all about flexural strength moment, right? We're going to design beams where we know the size, where we don't know the size, and if we are singly reinforced, as in only taking into account the tensile reinforcement, or if we include compression steel, so we're doubly reinforced. So first we're going to talk about some rules of thumb about locations. So, if you notice, the top shape is a continuous beam, probably a continuous slab, right? Floor slab over some columns. You have negative moment over the columns and positive moment at the midspans. And the purpose of tensile reinforcement, the steel, is to provide tensile reinforcement because concrete is not good in tension and it'll crack. So that is why we include tensile reinforcement. Now what you'll notice is you don't necessarily need continuous tensile reinforcement, right? If the moment gets small enough, if the negative moment gets small enough here in the middle, you don't need the reinforcement to go along the entire length, right? That you can save money because materials cost money, right? This continuous, and I apparently cannot write. You don't need continuous reinforcement. Well, you might not. Right. Depends on your flexural requirements. So the top, we have our deflected shape. Okay, it's going to crack midspan and over in the bottom and over at the top over the columns. This is our moment diagrams. We all remember those from structural analysis. And you can say, okay, I'm going to have tensile reinforcement in the bottom for these lengths, but I only need it in the top because you see it switches from positive to negative, and yeah, so you don't need it the entire length. You need it to be developed for a certain length, and that's a different topic, but develop the strength that it needs to have, but you don't need it along, you might not need it along the entire length is the entire point of this slide. Now what you'll also notice is if we're looking at like a section, we have our stirrups, maybe they look like that, and we have our longitudinal reinforcement inside. All right, typically you want to have 4, 1 for each corner if you're a rectangular section with I guess I could keep that, but right. We talked about that when we talked about concrete or compression reinforcement. One reason is just to anchor the ties or the stirrups. So that's where we want to put reinforcement. In terms of beam design, if we go to table 9.3.1.1, It's on page 129. Right. Design limits. Minimum beam depth. For non-prestressed beams supporting or attached to partitions or other construction likely to be damaged by large deflections. Notice this is dependent on deflections. The overall beam depth height, not the depth to the, not the D, but the H, the overall height, shall satisfy the limits in this table unless you calculate deflections. This is dependent on if it's simply supported, one end continuous, both ends continuous. So that would be simply supported would be right? One end continuous, right? Or both ends continuous. And we're only looking at like this span right here in the middle. Or a cantilever. It's based, your minimum height is based off of your length. Length divided by 16, divided by 18.5, divided by 21. That is, if you recall from like steel, oftentimes actually your deflection sometimes dictates your design. The strength might be fine, but the deflection. So notice that this is all based on deflection. If you also notice the little note down in there, expressions applicable for normal weight concrete and FY of 60,000 PSI. For other cases, as in if you have an FY of something else, or if you have lightweight concrete. There's adjustments that can be made. But this is just your minimum depth. Where'd it go? So. Right, and this is for your calculated deflection limits. Just saying, go to look at 24.2. If you want to do some more calculations. Let me see, can we click on that now? I don't even know where 24.2 is. So. Calculation of time-dependent deflections. I don't know, what do we got? That's the time-dependent factor, blah. We're not getting into any of that at all. We're just going to stick up here, good old page 129. That's your minimum depths. So let's see. Again, this is on page 129, and you'll notice, right, this is based on deflections. And to use this table, you have to have normal weight concrete and steel with a yield stress of 60 KSI. If not, there's modifications. If we want to remember, simply supported, which is our nice statically determinate beam, right? Just one span. One end continuous means we're looking at this beam, or the other beam, really, where this end is not continuous and this end is continuous. Both ends continuous. It'd be like if we're looking at like a 3-span. And we're looking at the center span. Right. And imagine these supports are columns. And then obviously I hope you know what a cantilever looks like at this point, but just draw those, or you don't have to, but I'll give you a second if you want to. So that is how we determine our minimum depth. Maximum is probably what your architect tells you. Obviously, smaller is better because it uses less. Smaller is probably better because it uses less material, but you know, you also need that moment arm for your for your capacity. So okay, concrete cover. I am looking at the bottom half of a beam where I have something like that, I don't know, and then 1, 2, 3, 4, 5, 6, 7, 8. I'm looking at the bottom half here. That looks like an angry person. Arr. Anyway. So, we have to have special spacing. We have to specify the spacing between the bars, between the bars and each other, and the bars in the outside world. So if we're talking about cover, we're talking about the bars in the outside world. Right? time we're talking about spacing between bars in a layer. Spacing. And spacing between layers. So if we're talking about concrete cover, it's specified in section 20.5.1.3, which is on page 382. 20.5.1.3.1. Well, 1.3. So 382. Oh, I got really close. Think about what might affect how much cover you need. Right. The biggest issue that we care about in terms of cover is how likely concrete, or how likely your reinforcement is to be exposed to water. Because if steel reinforcement touches water, it'll start to corrode, right? Or if water touches your reinforcement. So if we're looking at 20.5.1.3, these are cover requirements. Cast against the ground, and this is cast in place. It must be, if you're in the ground, you're at 3 inches. You have to have 3 inches between the outside of your beam and the first thing of reinforcement, which is probably your stirrups. So we're talking like to the outside. Okay? Not to the center, but to the outside of your reinforcement. So it needs to be 3 inches if you're cast in place with the ground. If you're outside, then you're looking at either, depending on the size of your reinforcement, and this is talking about your first thing that's going to come into contact. So this would be like your stirrups, and often stirrups are like number 4s. So you're probably looking at 1.5 inches generally. If you're not exposed to anything, again, you're at 1.5 inches. Looking at beams here, primary reinforcement stirrups. Now, actually, this exposed to weather might be your little longitudinal reinforcement, because that stirrup's not always going to be there, but if that stirrup is a number 4, so a half an inch, then it would be 1.5 plus 2 inches, so, or 1.5 inches cover plus half-inch hoop before it gets to your longitudinal reinforcement. So, yeah. So this would be 1.5 inches. The distance to your longitudinal reinforcement would be 1.5 inches plus 1/2 inch. So 2 inches. If that was a number 4. So really, this is a geometry problem. Like, as in, like, just draw things and add in dimensions and you'll figure it out. So generally 1.5 inches is what we're looking at, unless we're talking about like a footing. And this is for non-pre-stressed concrete. Further in the chapter, it talks about pre-stressed or precast. This is cast in place. Also starts to talk about, right, corrosive environment, like right now we're in pre-stressed, pre-stressed precast, deep foundations. Again, we're still talking about like probably 3 inches. If it's cast in place, corrosive environments, coated reinforcement, right? If you add an epoxy coating or something, it's probably going to add some protection, so you can decrease your cover to that. Although the epoxy affects the interaction of the reinforcement with the concrete. So your cover is based on your exposure to environment. Typically 1.5 inches, except foundations are. So beams, right, we're talking about a beam, so it's going to be typically 1.5 inches. So that's all about, right, that's in chapter 20, which that whole section is materials and durability, is part 6, materials and durability. So that's really talking about how do we make sure that we protect our materials, because that concrete's gonna crack. It's gonna allow some moisture in there that's going to corrode our reinforcement. Then this for our concrete spacing, when we're talking about the actual reinforcement and how it is spaced between itself. We're going to look at chapter 25, which starts on page 467. 467 starts chapter 25, which is our reinforcement details. Chapter includes minimum spacing, and that's where we're going to focus. So minimum spacing is based off of, for parallel non-pre-stressed reinforcement in a horizontal layer, so spacing between bars in the same layer. Clear spacing, that means the absolute clear, not center to center, but the clear spacing, shall be at least the greatest of 1 inch dB, right here, 1 inch dB, which is the diameter of the bar, or 4/3 the diameter of the aggregate. And they're talking about the aggregate that you use to make your concrete, right? Concrete is made out of cement, sand, aggregate, water, and then admixtures. So we're talking about the aggregate itself. This is for in a horizontal layer. So if you have, and it says has to be at least the greatest of, so the maximum of these three things is the minimum spacing. So if you have like a number 7 bar, the spacing can't be 7/8 of an inch. It's got to bump up to 1 inch, and so on. And then for parallel, that's so in the same layer, right? In the same layer. And then on the next one, it says for parallel non-pre-stressed reinforcement placed in 2 or more horizontal layers, reinforcement in the upper layers shall be placed directly above the bottom layers with a clear spacing of at least 1 inch. So if we go back to here, this section is, oops, right, this is 25.2. I wrote it down. I have a tab that says beams longitudinal reinforcement. So 25.2.1 greater than or equal to the maximum of 1 inch. The bar diameters 4/3 times the size of the diameter of the aggregate. So it's bar size and aggregate size. And then the spacing between layers, 25.2.2 must be greater than or equal to 1 inch. And again, this is, see, the clear spacing. Because we gotta have space in there for the aggregate and everything to get in there so that the steel can bond. Right, a little bit of bonding time. So, why do we need cover? I just said one. It bonds the reinforcement and the concrete. Cover slash spacing, right? On the outside, it protects the reinforcement from corrosion. It also, adding cover as an insulator, so it protects the reinforcement from overheating. If there's a fire, there's a fire, it might get to that reinforcement and cause it to soften a little bit, make it weaker. It also protects the entire beam from wear and tear, basically, right? Such as like foot traffic or car traffic. Probably more car traffic, but like on your slabs. I'm going to do a little example. Calculate D as in the depth to the centroid, which will be somewhere in here. And your minimum width of your section. So let's start with our minimum width. So let's assume this is just a beam. It's not cast against the ground. So if we look from the outside to the in, this is this DS. This is a 3/8 inch stirrup. So we have a number 3 stirrup. So my diameter of my stirrup is 3/8 of an inch. cover. So from the outside to the first seal is 1.5 inches. And I have that on both sides, right? My minimum spacing, I'll draw this in a different color. My minimum horizontal spacing is the maximum of 1 inch. My longitudinal bar diameter, or 4/3 the diameter of my aggregate. That's 1 inch. The diameter of my longitudinal bars. 3 number 9 bars on the bottom here. So the diameter of my number 9 is 1.128 inches. Four-thirds of my aggregate, 4/3 times 3/4 of an inch is 1 inch. So my minimum spacing horizontally is 1.128 inches. My next part is going to be something new. You see how I've got this bend in my hoop, right? Or my stirrup. Maybe it's the exact same diameter as my longitudinal bars, maybe it's not. What I'm going to do is look up what that bend geometry and dimensions look like. Okay, this is something that you're gonna have to do over and over again. Draw it out, think about it. This is on page, or it's in chapter 25, which is where we just were. 25.3.2. Okay. It's on page 470. That's hooks. This is inside bend diameters. if you look at this, let's see. Oops. This is the inside bend diameter for stirrups and ties. Table 25.3.2. If we are looking at a 90-degree hook, so that's what we're looking at right now, this is the inside bend diameter, so it's the inside bend diameter, right? We want our concrete, or our longitudinal reinforcement to nest in there as where it can. So we're going to assume that the centroid of the corner longitudinal bars is at the centroid of this diameter. So we want to know what the radius is of that. So it's just half the diameter. So the distance from the inside of the hook of the stirrup to the centroid is minimum inside bend diameter 4 dB, so 2 dB. Because we're at a number 4, a 90-degree hook, number 4, we're going from here, the inside of the stirrup, to the center of that bend. That's where we want to put our reinforcement. I realize it's kind of drawn the other way, but so we are going to go from, right, the inside to the centroid. Inside bend radius 2ds, and that is, it says dB, but right, dB, but it means the diameter of the stirrup, not the diameter of the longitudinal bar. Two times 3/8 of an inch, which is 6/8 or 3/4 of an inch. This is write this down. Stirrup bend. Table 25.3.2, which is on page 470. inside bend diameter for a number 3 is 4 ds. Place center of corner longitudinal bar at center of bend. Right? And that'll be fine. It needs to be, it'll be 3/4 of an inch, and half of a number 9 is less than 3/4 of an inch. So there's a little bit of gap. You can kind of see. You can kind of see there's going to be a little bit of gap. Right, that's the center. So you need from inside stirrup to center of your corner longitudinal bar is 4 ds over 2, so it's 2 ds because it was a radius, it was a diameter, and I need a radius, right? So I got the same thing on the other side from here to here. Same thing. So what am I missing? I'm missing my let's see. Missing my stirrup diameter because my cover goes from the outside of the beam to the outside of my reinforcement. That's where my cover stops. The next thing I know is from the inside of that stirrup to the center. So I just need, right, 3/8 of an inch. Same thing over here. And finally, this right here. This is a number 9 bar diameter, 1.128. This is actually, because this is the center to my outside, that's a 1/2 a bar diameter. Half of a number 9, because this right here is the other half of my number 9. Right? It's taken up by the center, by that bend. I'm placing my center of those corner ones at the center of that bend. The bend is 3/4 of an inch. Half of a 1.128 is not greater than 3/4 of an inch. Okay. So then I get to add, well, let's see, 1.128 divided by 2. But you can just do 1/2 plus 1 plus 1/2. So longitudinal bar so if you start to add it up, right, looks pretty colorful, huh? Let's see, my minimum width equals, I've got 2 covers, right, on either side. I've got 2 stirrups. I've got 2 bend radiuses, right? Radii. I've got a minimum spacing, right? 2 minimum spacings. I've got 1/2 plus 1 plus 1/2 longitudinal bar diameters, dBs, right? Got 2 covers. I mean, you could just go from one side to the other, but 2 covers, 2 stirrup diameters, 2 inside bend radii. Then you have 2 minimum spacings, because you have 3 bars, so you have 2 minimum spacings. Then my 1 center bar, dB, and then half of my 2 corner bars, so half dB plus half dB. So my minimum width, this is just to satisfy covers and spacings, right? 2 times 1.5 inches plus 2 times 3/8 of an inch, that's my stirrup, plus 2 times my inside bend radius, which is 3/4 of an inch, plus 2 times my minimum spacing, 1.128 inches, plus, I mean, this is 2, right? Half plus 1 plus half times my number 9 diameter. So the minimum width of my beam, that's my minimum. 2 plus 1. 9.76. So I'll probably round up to 10, but that's my minimum, right? If you end up having a wider beam for some reason, if you end up having a wider beam, that just means that spacing, the red, will just get bigger. Well, and your hoops will get wider. You'll probably keep the 1.5 inch cover. So just that red space between your longitudinal bars will get bigger. Okay. So study this, see what questions you might have. That's for your minimum width. Okay, we did this. Check. How about calculating your D? Hopefully this is something y'all figured out, but I should copy that. Yeah, I don't really want any of this. Okay. So that is your width. That's probably the most confusing part because of that bend diameter. So now if we look at D, now we're looking vertically, right? So again, we have our cover, which we've already figured out is 1.5 inches. That is the distance from here to here. We have our stirrup diameter, which is, it's a 3/8 of an inch. Our cover is 1.5 inches. Now this is where in the horizontal we took into account the bend diameter, the bend radius. In vertically, it's just resting, right? It's just resting. So the distance, what color would I make that? the distance from here to here is just half of a number 9. So half of 1.128. And this is the other half. Right? So this whole thing is diameter of a number 9. So 1.128. My minimum spacing if I looked it up, if you remember, between layers is just an inch. Horizontally, you need more space. Vertically, you don't. Right? I was back on page 467. This is the horizontal layers. This is for 2 or more layers. Shall be at least 1 inch. So, and then this is just my number 8, which is 1 inch to here. Could have made a different color because it's a different bar, right? I have number 9s and number 8s. So now I want to figure out, right. I'm going to measure from the bottom. I'm going to find the centroid, right? I'm going to call this layer 1 and this layer 2. And I'm going to find Y. It's the location of my centroid. So Y is my area of layer 1 and my Y of layer 1 plus my area of layer 2 and my Y of layer 2 plus area 1 plus area 2. So let's see. Area of layer 1. I have 3 number 9s, right? We'll just write over here. Area 1 is 3 number 9s, so 3 times, I think that's a square inch. Yes. Area 2 is 2 number 8s, so 2 times 0.79, whatever that is. distance from the bottom to the center of layer 1 is your cover. Is your cover plus your stirrup plus half of number 9, right? We're going from the bottom to there, there. So I've got 1.5 inches plus 3/8 of an inch plus 1/2 of 1.128 inches. The distance to the centroid of the other one, right, is y1 really. y2 is y1 plus, alright, I'm at the centroid of layer 1, so I need another 1/2 number 9 plus my minimum spacing plus 1/2 of a number 8. Right. I went from here, the cover, my diameter of my stirrup to the center, and now I'm just going from here. I need another 1/2 of a number 9, my minimum spacing, and 1/2 of a number 8. Plus 1/2 of a number 8, which is 1 inch. Alright, that's 4.5. 1.5 plus 3 divided by 8 plus 4.5. Okay. Should be even better. So, if I want to find the centroid, I've got 3 inches squared times 2.439 inches plus 4.503 area 2, 1.58 inches squared times 4.503 divided by the total area. So the distance from the bottom should be 3.15 inches. And D is just the height minus that centroid, right? So my height, I don't know, what did I say? Like 24 inches? 24 inches minus 3.15. I just found the centroid from the bottom and then subtracted it from the overall height. And that's D, like the distance from your extreme compression fiber to the centroid of your tensile reinforcement. If I were trying to find DT would be 24 inches minus Y1, right? Y1 being the centroid of layer 1, Y2 layer 2. You're doing that. dt equals h minus y1 is 24 inches minus 2.439 inches. Whatever that is. 21 point something. Alright, that's just the distance to the extreme tensile fiber that you, or extreme tensile reinforcement that you would use for your phi calculation. Finally, gonna wrap it up with some reinforcement location rules of thumb. can kind of see already. For beams, with one layer of reinforcement, your D is about your H minus 2.5 inches. You might have noticed that on some of our examples. It's just an easy rounding, right? And if you have 2 layers of reinforcement, it's about equal to H minus 3.5 inches, right? Probably because you're could have spread those out. Could I? Okay, 1 layer of reinforcement. Subtract your location of your central edge, about 2.5 inches from the bottom of your beam. 2 layers, probably 3.5 inches, right? This one, right? Our DT 24 minus 2.439. That's just about 2.5 inches, right? And same thing, let's see, we subtracted, that's less than 3.5. But, you know, ballparks here. For slabs, with spans of less than 12 feet, D is about equal to the height of your slab minus 1 inch. And greater than that, about 1.1. The beams are really what we're going to focus on. So when we're starting out with guessing about things, these are starting out guesses. Okay? Next up, we're going to do an example.